All right, today we're cracking open one of the biggest unsolved mysteries in all of physics. Think of it like a cosmic cold case, where our two best theories of how the universe works are pointing fingers at each other. And the crime scene? It's a black hole. Let's get into it.
So you have to understand, there's this one fundamental rule that everything in physics is built on. It says that information can never, ever be destroyed. Now, when we say information, we're not talking about words in a book. We mean the unique, nitty-gritty quantum details of every single particle, its location, its speed, its spin. You can scramble it, you can hide it, but you can't delete it. It's got to be preserved forever.
And that right there is the question that blows everything up. Because what happens when this supposedly unbreakable law goes head-to-head with the most destructive force we know of? Well, you get a paradox so deep, it has kept physicists up at night for almost half a century.
To really get what's going on, we have to go to the scene of the crime. We're talking about the edge of a black hole, a place where our understanding of physics is stretched to the absolute breaking point.
This boundary is called the event horizon. Seriously, just think of it as the universe's ultimate one-way door. Anything that crosses it, a star, a planet, even a beam of light, is gone. It's pulled into the singularity at the center. And according to classical physics, it is sealed off from the rest of the universe forever. And for a long, long time, we all just thought, well, that's it. Black holes were cosmic vaults. But then, Stephen Hawking had this incredible insight that changed everything. It turns out, these cosmic prisons, they leak. Yeah, it's wild. By applying the super weird rules of quantum mechanics to the edge of a black hole, Hawking realized they had to be giving off energy. They actually have a faint glow, a kind of thermal energy, that of course we now call Hawking radiation.
So how in the world does this work? Well, the vacuum of space isn't really empty. It's constantly fizzing with these little pairs of virtual particles that pop into existence and then immediately cancel each other out. But right at the knife's edge of the event horizon, one of these particles can fall in while its partner escapes. And here's the kicker. These particles were entangled, meaning their fates were linked. So the particle that escapes carries a little bit of information away with it. And that stream of escaping particles is Hawking radiation.
Now, this constant trickle of escaping particles means the black hole is losing energy and therefore mass. So over an unimaginable amount of time, we're talking trillions upon trillions of years, the black hole will shrink, and eventually, just poof, it evaporates into nothing.
Okay, and this is where our mystery gets really, really weird. The black hole is gone, but what about all the information, all the stuff it's swallowed over its entire lifetime?
Here is the absolute heart of the problem. The Hawking radiation that leaks out, it's mostly random. It's thermal. It can tell you how hot the black hole was, but it can't tell you if it ate a star or a spaceship. Most of the original specific information is just missing.
And there it is. That's the Hawking paradox. If the black hole disappears completely and the radiation it spit out is basically generic, then all that unique information has been permanently deleted from the universe. And that breaks that fundamental rule we started with. So, what gives?
What this sets up is a heavyweight tidal fight between the two pillars of modern physics. You've got Einstein's general relativity, which says nothing escapes a black hole, period. Information is locked in. But then you have quantum mechanics, which says information can never be lost. They can't both be right. Something has to break.
This puzzle has been a massive headache for physicists for decades. But it's also led to some of the most creative, out there ideas in all of science. So let's look at the lineup of suspects, the top theories trying to solve this thing.
First up is an idea called complementarity. It's a really clever take that basically says the answer to the paradox depends on where you're standing. It's all about your point of view.
Okay, stick with me here, because this is a bit of a mind bender. The theory goes like this. If you're watching from the outside, you see the information get kind of smeared onto the event horizon and then slowly leak back out as Hawking radiation. But if you're an astronaut actually falling into the black hole, you'd sail right past the event horizon with the information, no problem. So you have two copies of the information. But since nobody can ever be in two places at once to see both copies, the no cloning rule of quantum physics isn't actually broken. It's just two different perspectives of the same event.
Now that's a pretty elegant solution, right? Well, not so fast. Physicists eventually found a potential hole in it. They realized a clever observer might be able to see both copies, which would be a huge violation. The fix for this problem is a lot more dramatic. This idea suggests the event horizon isn't some calm boundary line. Instead, it's a raging, high-energy wall of fire. Anything that tries to cross it, astronaut, star, whatever, gets instantly fried. It's a brutal solution, but it works, by violently severing any connection between the inside and the outside, making sure no quantum rules get broken. But, man, it would totally change how we think about black holes.
And that brings us to our final suspect. This is the newest theory on the block and maybe the most fascinating. It suggests the answer is hidden in these bizarre quantum connections between the deep inside of the black hole and the radiation way, way outside.
The latest calculations point to these things called islands deep inside the black hole. These islands hold the supposedly lost information. But here's the crazy part. It seems these islands are quantum entangled with the radiation that escaped long ago. In a way, you can think of these islands as poking just a tiny bit outside the event horizon, creating a sort of bridge. This bridge connects the information on the inside with the radiation on the outside, proving it was never really lost to begin with.
And how far do these islands poke out? Get this. For a giant black hole, millions of times bigger than our sun, we're talking about a distance that is about the length of one single atom. It's an unbelievably tiny window to the inside.
But that's the thing that makes this so exciting. That distance, as tiny as it is, isn't zero. It means that it's theoretically possible that some super advanced technology in the future could actually probe that boundary and measure the information directly. We could finally crack the case.
You know, at the end of the day, the Hawking paradox isn't just some abstract puzzle. It's a massive clue. It's the universe screaming at us that our two best theories, general relativity and quantum mechanics, are incomplete. Solving this paradox will almost certainly lead us to a new, deeper theory of everything, a quantum theory of gravity.
And that just leaves you with this incredible thought, right? The key to understanding the true nature of reality, of space and time itself, might just be locked away in the darkest places in the cosmos, just waiting for us to find it. Thanks for joining this explainer.